Okay, so I will introduce our last speaker of today. Well, what can I say about Daniele? I met him in Kent State. We were both doing our PhD in Kent State. I was a student of Richard Aaron and he was a student of Joe Distel. And so we had a great time there, like mathematically speaking. Also with, we met a lot of friends there. We made a really nice group. We made a really nice group, the PhD students, the graduate students. And from there, we just kept being friends, a long friendship that will continues and will continue. And okay, so Daniele will speak about on certain classes of first pair functionals. Go ahead.
Okay. Thank you very much for this introduction, and let me thank all the organizers for this fantastic conference, fantastic place, and especially I would like to thank Paco for the invitation. Okay, I'm the last speaker. My position is nice because for sure at the end of my talk nobody asks questions because people want to go for lunch. Okay, let me okay, this is a talk about joint work with one of my students, Jeremy Mirmina. He was first in Catania, but now he moved in Pisa. And let's recall classical definition. Maybe you teach to undergraduate student this definition. If KD is a complete metric space, a function from K to R is called of the first Baire category if you can approximate point-wise on K by a continuous sequence of function. And let's collect the all first Baire category function by B1 of K. Okay, just let's mention the really old result of Baire, that a function is first Baire function if and only if it's a restriction to every closed subset of K as a point of continuity. This is really classic, and also this is another classical corollary. F is B1 of K if and only if is continuous at a dense set of points. Okay, but let's go to Banach space. Okay, suppose X is a separable Banach space. And then we know that the uniball of its dual, and all with the weak star topology, is compact measurable space. And then it makes sense to consider all continuous function of B of X star. Then we know that X can be isometrically embedded in the C of B of X star. And also the B dual can be embedded in the space, the Banach space of all bounded affine function of this ball in the way with the supernorm. Then, since X is in C of Bx star, then one can define B1 of X. It's not like functions, Baire 1 function in the ball, but we collect all the functionals in the B dual such that there exists a bounded sequence on X such that X star star can be approximated pointwise on the dual ball by this sequence Xn. And Jean Bourgain, a really young Jean Bourgain, proved that an element in the B dual is in B1 of X if and only if is just a first Baire function. You can approximate by continuous function on the ball. This is just equivalent. That's why the notation B1x or B1 of the ball. This justify the notation. Okay, and finally, let's introduce also the BSC of X, the subclass of we consider difference of bounded semi-continuous function on the unit ball of the dual. This notation, okay, we introduced this notation for some classical result, like X is a reflexive if and only if the B dual can be embedded in the space of continuous function of the unit ball of the dual. Okay, and also let's recall this classical result, really nice result was proved in the 70 by Odell, Rosenthal, also Rosenthal, that X does not contain a little one if and only if the B dual coincide with the first Baire 1 functionals. And also, okay, actually, before the Odell-Rosenthal, Besaga and Puglisi also proved that the X does not contain C0 if and only if actually, if you remember the space of difference, bounded and continuous function of the ball, unit ball, coincide with continuous function of the unit ball of the dual. This was proved in 1978, really old result. Okay, related to the space, Oscar Rosenthal writes the following question. Okay, suppose we have a functional in the B dual which is first Baire functional. And is it also possible to approximate this functional by a pointwise, of course, by a sequence of elements on X, such that the closest span of Xn does not contain a little one? Is it also possible to do that? Or the same, the second question by Rosenthal was, it can be, we can do also approximate a one Baire functional by a sequence of elements of X, pointwise of course, such that the closest span of Xn has separable dual. Okay, and it's convenient to introduce just notation. We collect B10, the functional in B1 of X, such that the approximation can be made such that the closest span of Xn has separable dual. And we also collect by B11 of X the functional in B1 of X, first Baire functional, such that the approximation can be done by a sequence Xn in X, so that the closest span of Xn does not contain little one. And by the definition, we have this chain of inclusion. That's the lower level, is the space X. Then you go to B10, B11, and of course our definition of B1 of X, the first Baire functional, of course in the B dual. And let's see the answer of the Rosenthal question. Actually was positive, was proved also by Bourgain. Bourgain proved that this is true if the function in the B dual actually stay in this, is different of bounded semi-continuous function on the unit ball of the dual, still in 1980. A negative in general also was proved by Bourgain in a different paper, still in the same here. Actually, the example Bourgain is really extreme. Extreme in the sense that the example of Bourgain is a Banach space XB such that B10, B11 coincide with the lower level, with the space. And the space of B1, or the first Baire function, is different, is higher. And let's recall another definition. A Banach space is said to be weakly sequentially complete if X, the B1 of X, coincide with the lower level, with X. And in connection with the above questions, let's recall this theorem, classical theorem. If X is a separable infinite dimensional Banach space, if X has the sure property, then X is weakly sequentially complete, it has no reflexive subspace. And the second part claims that if X is weakly sequentially complete and has no reflexive subspace, then X is hereditary little one, which means a little one is everywhere in the space. Every infinite dimension subspace contains little one. And then if you consider the Bourgain space I mentioned before, this space also provides an example of Banach space such that the converse of the second part of the part B of the above theorem does not hold. Actually, joined with my student. We use the same technique of Bourgain, that we provide another example such that also the converse of the first part of the theorem doesn't hold. The part, in the paper, Bourgain just sketched the construction, but it was really hard to follow. Actually, we try to make the construction with more details. Okay, let's see setting or sequence of Banach space. Actually, we construct by induction a sequence of closed subset of 0, 1 with cardinality the continuous, and a sequence of actually the extension operator. Isometric embedding is CK high in C01. And for each here, we said that if you fix for each I, you fix any closed subspace of CKA, and you fix any sequence in Xi such that with norm 1 which generate the space, you are free to choose any sequence of Banach space Xa, and also in the lower level for I equal to 0, we need this inequality, and also we require that for each I there exists an operator from Xi plus 1 to Xi which map the element in the level K element in the level I plus 1 to the corresponding A high K, is such that this operator is strictly singular. Strictly singular means is never in every part in Xi plus 1 is an isomorphism. Yeah, anytime you fix infinite dimensional subspace of the Xi plus 1, the restriction is not an isomorphism.
The first.
Well, okay, now we are free to choose this sequence of Banach space such that also you have this sequence of associated to this sequence of operator, not strictly single operator. Strictly single operator. And then we consider the element AAK, we consider is remember, AI was just you put inside in C01, and then you consider Fk, the summation of this 1 to the high to Fak, the summation over A. And then consider the closest span of this sequence. What we prove that if every sequence we have chosen, Xi, is weakly sequentially complete, then the space we obtain, X, is also weakly sequentially complete. And in any case, independently how you choose Xi, X you obtain, the space X you obtain in this construction is every time is hereditary little 1. And now, okay, we just choose the sequence. Our sequence of Banach space, okay, here we say Y high is just little p with the index I plus 2 over I plus 1. And also, okay, as sequence in this little p, we consider is Schauder basis. Plus, okay, the operator now exists and also is strictly singular because it's a classical theorem that the space little p with another little q is always, they are totally incomparable. That means there is no infinite dimension which is isomorphic to a subspace of little p. And then we are sure that this with the choice of this sequence Y high with this kind of little p, okay, we satisfy all the conditions we required before, and then okay, of course, this space generated by this sequence Yi is by the previous theorem is hereditary little 1. Of course, each sequence little p is greater than 1. Each space is reflexive and then easily is weakly sequentially complete. And then by the previous theorem, the space we construct is also weakly sequentially complete. Okay, it can be checked that this space is not a sure, doesn't have sure property. Okay, just with. But, okay, we don't prove that. Okay, let's go. let's come back to Rosenthal questions. Okay, Rosenthal, okay, does it always true that B1x equal to B10, or B1x is also always equal to B11 of x? This, okay, the Spice-Bourgain example, where this extreme situation holds, we construct a new example, actually, but also, to be honest, we used a lot all the ingredient of Bourgain paper. Okay, we construct x equal to space of continuous function in the Cantor set. And at the end, we found out that B10 and B11 actually are never, for this x, they are never vector space. And then that means the equality cannot be true. Okay, let's see something. We'll just let's mention the ingredient we use. Okay, a sequence or real value function on a set C, we said that Fn converges strictly on a subset A if this series is point-wise is convergent point-wise on A. Strictly converge. And of course, strictly converge implies point-wise convergence. And let's denote by x b of x star the set of all extreme points of the unit ball of the dual, and with the weak star topology. And the first, let's introduce also this B1 SC of x. We collect all the functional x star star such that x star star is point-wise living of a sequence xn in x, but such that xn has to be strictly converged on the extreme point of the unit ball of the dual. And what we found out at the end is this new set B1 SC is inside the B10. And also we consider K2 to the omega, the Cantor set. We consider, we denote by KRS, the system of Canton interval. For a function, if you consider you have a function on the left of this KR1, you can extend to the other part on the right by this small trick. And by induction, we construct a sequence IR and BR of disjoint G delta set in the KR1, and a function phi which is in the classical sense of first Baire function, such that is 1 is on AR, is -1 on BR, with the sup norm equal to 1. And for each R, you consider just the extension of those phi R to the other part on the left, where when t is inside the KR 2 to the R minus 1 and 0 otherwise. And then finally we define capital phi, the summation of 1 over 5 to the R of those phi R arrow, and psi, capital psi, the summation of 1 over 2 to the R of those psi R, which are first Baire functions, okay? And let's also recall, because we are considering what? We are considering on the Cantor set, we are considering first Baire function, but this is a small trick. All of those first Baire functions in a classical set can be extended in Baire 1 functionals in the B-dual. How? Just considering the extension of this Coquet theorem. Just define in the B-dual, because we are working in CK and the dual is the measure space, and just define as function in the B-dual like integral on K of phi on the nu, and this extension is unique, it's a classical theorem. And what we found at the end was this extension, those extensions for capital psi, capital phi are such that the capital psi, the functional in the B-dual of capital psi, set in the B1 as C, which is the smallest set. The summation the sum of phi hat and capital psi hat set inside in B10, but at the end, the phi at capital phi is not in B11. That means the sum of two elements in B10, or of course in B11, are not in B11. That means those are not vector space. And then it follows that those set for this particular space is contained strictly X, and is contained strictly in B1 of X is also an example. But we managed this space, which was much easier to describe the family of Banach space. Okay, let's recall that classical Banach-Mazur theorem, that every separable Banach space is isometrically embedded in C to the omega, and we consider F C to the omega, the set of all closed subset of C to the omega, and we keep this set of closed subset, the family of those closed subset, by the Efros-Borel structure, which we consider in some sense the open set are generated by an open set in C to the omega by this condition. We collect all the clauses which touch this open, fixed open. And we denote by S of B the subset of this family of closed subset of C to the omega, consisting of all linear closed subspace of C to the omega with the relative Efros-Borel sigma algebra. And Bossard in 2002 proved that this SB is a Borel subset of F of C to the omega. And then, okay, since this Bossard theorem, anytime you have a property for a separable Banach space, you can study like the script set family. In the script set theory, you can describe if this family, this property is a Borel or not, or is analytic set, and so on. Actually, using this, this family, we proved that the family of all separable Banach space such that the inclusion is strict. The inclusion between B11 and B1, but the same B10 and B1. When it's restricted, this is not Borel. Actually, we proved this family is sigma 1 hard. Those properties in particular implies those are not Borel. That means the Bourgain example, as well as the example we presented also, we introduced it, are not isolated. That means since this family is not Borel, that means you have a lot of several Banach space with such a property. And okay, maybe I don't have so much time, but let me also ask this question before we leave. But we don't know if there exists X separable Banach space such that B10 is strictly contained in B11. That means what? That means anytime you approximate an element here, a functional, with a sequence, that means X star, remember, that means exists Xn in X such that the limit of Xn of X star equal to X star of X. For any X star, let's say the unit ball. Okay, it's such that the span, closed span of Xn does not contain little 1. Is it possible to approximate this? Okay, I don't know. is it possible to approximate a functional with a sequence such that the closest span of xn doesn't contain little one, but anytime you approximate with any sequence on x, this closest span has separable dual. Actually, there is work by Ted Odell, which is related but does not answer this question. But I don't know the answer. And thank you very much for your attention.
Okay, thank you very much. Very strong results. A very interesting question. Does anybody have a question, remark, comment?
Okay, my conjecture was false.
Okay, so I think your results are just for separable Banach space, right?
Yeah, for sure.
Yeah, because you need the metrizable
Separable
space.
because you need that the unit ball of the dual is metrizable.
Yeah, so do you think is there a way to generalize the sequence convergence to a certain cardinality?
Actually, people was done by, was a paper in the 80s by Richard Haydon, maybe Odell, and maybe Rosenthal. People already studied this kind of question when the Banach space is not separable.
Okay, so
you already have. Yeah,
okay,
I can give you the reference.
Okay. Okay, and also, is this B10 dense in B1x?
Sorry, B10?
Yeah, B10 of x. Is this dense in B1x? Or? Because, yeah, I think you want to say actually, it's a subset, a proper subset.
Yeah,
is it
subset.
dense?
Dense, let's say, but actually I don't know. Yeah, I don't know, because you require that anytime you require that the span, closest span of xn, you consider the dual is separate. And to be dense, to check the density.
Yeah, whether the closed linear span, because you say, because what you proved, okay. I think the example you gave is not a subspace or something.
Okay, you have density because you have this one, no? And you have density from here to here, and then you should.
No, X is just weak star dense, right?
Sorry?
X is just weak star dense, but not.
Yeah. You ask me. Okay, dense in norm.
Yeah, of course. You are not saying weak star density. There's no.
I don't know. Okay, because I was thinking about always considering weak star topology.
Yeah, because your counterexample just shows that it's not even a subspace, something like that.
Yeah.
So if you take the linear span or
I don't know the answer. Okay, I don't know.
Okay.
Maybe I never thought about this question.
Okay, thank you.
Any other question? Okay, so let us thank the speaker again.